Hello and welcome back for another exciting presentation, this time on glacial geomorphology, or learning how glaciers have really changed our landscape. This is an exciting presentation for me because uh, it, when I was a student, I didn't understand the impact that glaciers had on California's landscape. We have already acknowledged that California is a fantastic and amazing place to live, but it was hard for me to comprehend that California had a glacial background and not just far away from us physically, that there's been evidence of glaciation very close and in some of the landscapes that perhaps you even love yourself. And to learn that this very large process took place is really exciting. So that's what we'll be discussing in this presentation. To begin, there's a photo of me. I'm pointing here at this mountain peak up in here. This is actually a glaciated landscape in California. This is Lake Sabrina outside of Bishop, California. Here we can see a horn, a pyramidal peak that's been carved and plucked by ice. Here we see this nice big rounded amphitheater shape, a glacial lake. We have some what they're called arêtes and coals and all kinds of different features that you'll be able to distinguish later on in the presentation. But this is one of my favorite places to visit, especially on field trips. So mostly because you can see so many of these features within that landscape, makes it very exciting. So let's start introducing what glaciers are. Now, what is a glacier? Well, glaciers are unique in the sense that they're made up of fallen snow. So we're talking not just, it snows outside, you look outside and go, oh, look, there's a glacier. We're talking decades on decades, if not even centuries, of snow that has been able to withstand melt season and be able to then compact slowly into a massive block of ice in that sense. To that point, most of the oxygen does get squeezed out. I like to think of ice, like your ice maker at home. You have two types of ice. You're going to have that ice that's super clear because there's not a lot of oxygen trapped within it. And then you'll have that ice that looks more white because it's been broken down because the oxygen has broken the crystalline structure down. So in this case, because of pressure, it's able to push a lot of the oxygen out of that ice. Now, that being said, glaciers can be small, maybe the size of a football field, but they can also be quite large, perhaps the size of a continent or even more. In fact, scientists have been able to observe and interpret interval sessions in which the entire Earth had experienced what we identify as snowball Earth, where essentially the North and South Pole froze over and began freezing all the way until it got to the equatorial zone. Well, let's back up a little bit here too. Here's another photo, same place, Lake Sabrina during the winter field trip that I did. How much ice is there? Well, only about 10% of the world's land, the landscape, the topography actually has ice on it. So we're really not talking about a lot of ice that is in existence today. But that being said, two-thirds of all the fresh water available to us is found within ice. So it's, although it's not as plentiful as we would like to have, the ice, it's still a very important and valuable resource for water, right? For storage, because that's the best type of storage you can have. It's not being stored in a reservoir, it's not being stored in a lake, it's being stored in a place high up in a mountain that then feeds our river systems and things like that. Well, I've mentioned that there have been some patterns. So looking at glacial periods in Earth's history, well, scientists have learned and through observation and interpretation that the Earth experiences episodic climatic changes, all of which are directly associated by glaciers. Well, uh, that being said, you probably have seen a diagram similar to this. There's many different ones out there. This one I picked in particular because this is looking at just the average global surface temperature. So this is going back in time. So we're going back 60 million years. We're seeing that this is a degree difference within here. We're looking at really just, what is that, 5, 10, 15, 20 degrees Celsius difference. So we can see that there were times when things were warmer. We can see when things were colder, that they got warm, cold, warm, cold, warm, cold, and they got a lot cooler. We're actually, as I said before, we're kind of we're in the middle of a glacial period. We're actually exiting a glacial period. So we've been significantly colder before, but we've also seen that we've been warmer before as well. So this is not zoomed in, so you would see that we've gone all the way up, to here, where this little line is up here. So we're actually making a very dramatic increase, very quicker than we've seen across the spectrum of time. So yes, if we're leaving a glacial period, it's still pretty warm, which should put that in perspective as to when we say that it could be warmer, how much warmer that warm really means. we do acknowledge that based on this graph alone, that things on our planet would have been very different 10,000 plus years ago, looking back into the the Pliocene, or even, well, Pleistocene, which is a little bit more recent for us. This is, oh, sorry, Pliocene, and the P is Pleistocene. Well, that being said, we've now also observed that Earth has been warm enough and long enough to be ice-free longer than it has over its time having ice on it. So we've had throughout the grand time scheme, we've had more times of warmth than we have of cold. Uh, how do we know that? Well, I'll talk about that in a moment. Now, what's interesting about this is that you obviously have heard that climate is changing, right? You've heard the phrase global warming. You've heard climate change. They're two very different things. We'll work through that within the modules. But when it comes down to science and the facts, is that we see that there are patterns of warmth and cold. Yes, the planet does that. So is it fair to say that we know as scientists that the Earth was on a warming trend before humans were even doing what we were doing? And the answer is yes. Yes, we do know that the Earth was on a warming trend. Okay, but the thing that we cannot negate is that because of human interaction with the environment, we have accelerated that change. So what's interesting about that is I've always compared this in my classes to people who were born and lived through the 1960s. The 1960s, sex, drugs, rock and roll, right? So, looking at someone like my dad who lived through the 1960s, party animal, had like 5 different cars, and we go cruising. He was a surfer, never wore sunblock, partied hard, right? Well, those people who partied hard now, as we're finding, they're dealing with skin cancers, or dealing with all kinds of health conditions, because the things that they did when they were younger really accelerated their illnesses as they got older. Think about smokers, right? People who smoke their whole lives, they're cutting off time of health within their lifespan, right? And that's what we're seeing here, is that the Earth partied really hard, and now we're trying to feed it vitamins and try to find ways to get the Earth to kind of get back into health. But what's interesting, living through the 2020 pandemic of COVID-19, is that we're now observing, and we'll have to learn to interpret that data, that because of people staying at home, people not driving, people not manufacturing, people just not eating out as much. So I guess all of these things that would otherwise induce greenhouse gases, would induce the amount of CO2 that's being emitted and things along those lines, that we're starting to observe weather patterns starting to kind of almost redirect themselves. We're starting to see the planet almost like healing itself in a sense, which is not something we had anticipated could occur, especially this fast. We're looking at when this is being recorded, about an 8-week span of the stay at home, and so this will be something very interesting to observe in the future. As we've established earlier on, understanding climate, we can't understand climate just off of today's data, that we have to look at the long term, 30 years of data. So that kind of brings me back to this, well, how do we know this? Well, one of the easiest ways we can do it is ice cores. Ice cores are fantastic time capsules of time, knowing what has occurred. So ice cores tell scientists about what the temperature, precipitation, humidity, the types of gases that were available within the atmosphere. Why? Well, because we're able to then go into this core, pull out within these itty bitty microscopic bubbles, and pull out what the atmosphere would have been like as it was trapped. It's like a water bottle, right? That you capture air, you seal the water bottle, and everything is kind of trapped inside. So this is a zoomed in image of an ice core. So we can see here that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is during the 12th. So there's about 11 and a half years worth of data. This has been zoomed in a lot. So they're able, like tree rings in that sense, looking at what happened during this time. So essentially each layer provides a time machine full of information about our past. This is an ice core right here. This is a real one. This dark gray area is really unique. This is actually a volcanic ash deposit that dated 21,000 years ago. So this is from, shoot, it's not Went. West Antarctica. That's a volcanic ash deposit from 21,000 years ago. So we're able to do that. Now, is this seamless? Well, no, because if you have a large warming trend, you lose layers of time. So what we do is we have to, kind of piece, it's the missing link. We have an ice core here, this is the data we have, and we can see there's perhaps gaps. So we keep accumulating that data until we can fill in the gaps. So that being said, taking ice cores from around the world in different locations, we've been able to successfully go back 1.5 million years. That was while the Homo erectus was still walking the earth. But why only that far? Well, that's also a good question. It's because we don't have data from farther beyond that, right? So if we go back to the diagram and we look at the highs and lows, we'll see that the climate was very different at those times. So this is kind of an interesting thing. This is just one example as to why, but it's probably the easiest to explain, is that we technically take those little bubbles, we stick a needle in there, pull the bubble out, and go, okay, well, if there's more CO2 in that bubble than what we have by parts per million in our atmosphere, then the more carbon dioxide, the warmer the temperature trends seem to be, which makes sense. How do we know that? Well, the warmer, when we look geologically, times in which there were a lot more carbon dioxide and other greenhouse gases in the atmosphere, that's when we'd go through things like the Carboniferous, where things just got really, really big. Looking at the Cambrian explosion of life, where dragonflies were 6 foot in length. So we find that this really does, that warm humidity does induce the growth of vegetation and things along those lines. So I thought that was kind of interesting nonetheless. Another way that we can do this is math. We'll make this as simple as we possibly can. Milankovitch was a mathematician. He came up with these 3 cycles in which we know that the Earth has gone through, and then they were able to take these cycles and then transplant them onto that diagram we saw on the 3rd slide. So what he had figured out is that the Earth goes through a collection of cycles within the movement, which can be observed in Earth's climate over thousands of years. So we can see that there are 3 types of Milankovitch cycles that the Earth goes through. We'll start here at eccentricity. There's also one called tilt and one called precession. So what does this mean? Well, we'll go through each one. Eccentricity means that we know that the Earth is in rotation around the sun. Okay, we know that right now we have the aphelion and the perihelion. The aphelion is when we're farthest away, the perihelion is when we're closest, but those distances fluctuate, and we know that. Well, there's also been times when the eccentricity, which is that distance, that this elongated piece, changes to perhaps even maybe to a closer circle, because we do know that although we do have times in which we're, 5 million kilometers closer or farther away from the sun, that distance does play a role on our climate. It does play a role on the amount of energy received by the Earth. So what if we were then equidistant and then you kind of leveled it out so you didn't have this level of extreme? We find that those patterns happen every 100,000 or so years. So that does make a change. Another one is the tilt. We know that we're currently at 23.5 degrees tilt, but it has ranged between 21 and 24. Well, what does that do? Well, the tilt, remember, the tilt of the Earth is what distinguishes our seasons with our special lines of latitude, the Tropic of Cancer, Equator, and then the Tropic of Capricorn. Well, what if that were to change? Well, if those tilts change, then we'd find that some areas would have darkness for, instead of just being 2 or 3 months out of the year, it could be even longer, 6 to 8 months out of the year, or vice versa. There could be times in which parts of the Earth will have 24 hours of daylight for months and months and months on end, instead of having a split cycle that we have now. So that's one. The other options is the last is precession. It's easily compared to a top. You spin a top and it spins, and at one point it starts to kind of do this thing. It starts to wobble a little bit, and the Earth does have a small wobble to it. It happens every 19 to 24,000 years, where instead of being tilted this way, it's still going to remain at that tilt, but just kind of the direction in which that tilt occurs begins to change. And so we've got these different cycles. So anyway, very simplistically, precession, you've got its obliquity, eccentricity. Looking at these, which is part of the tilt. Looking at these 3 here, we can see that there are patterns in which they occur. Looking at stages of glaciation, so you start putting it through here, you see that there are patterns of glaciations when these would have occurred, so either maximum or minimums, which is pretty cool. So Milankovitch, mathematician. There's some videos about it within the Canvas modules that will kind of help explain more if this is something that's interesting to you. Well, how do glaciers work? Well, We know that glaciers are a large continuous body of accumulated ice. We're looking at hundreds of years of age. But the balance of ice is balance between accumulation and wastage. So I always compare like those, people who work out, your gains versus your losses. So if you're gaining more than you lose, then the glacier will grow and advance. Or if you're losing more than you're gaining, then the glacier will begin to shrink. So a couple key words to point out. First one is powder. Powder is a phrase that we use for really fresh new snow. If you've ever been somewhere with fresh new snow, you'll notice it's very dry. It's very crystally, it's fluffy, it's the perfect snow cone material. And that's because it hasn't had an opportunity to condense and take that ice and move it more into a liquid state. So it's very dry. It's mostly air that's been trapped within that powder. The slushy stuff that we're most familiar with is, what we identify as snow is not great snow. Especially if you're a snowboarder or a skier, you know the difference. We have a phrase called firn, F-I-R-N. Firn is a phrase that we use for snow that's been able to celebrate a one-year birthday. So it's been able to withstand a winter and a melt season and make it again towards winter again, and it was able to hang on. And that's really the beginning of a glacier. And then an iceberg, which I'm not sure why that space occurred there, but I'll fix it. An iceberg is just essentially a piece of ice that has calved, which means it's been broken or cut off, and now is floating in the ocean. And we'll talk more about that later, but there's a great video called Chasing Ice. It is a documentary about the largest witnessed calving event ever seen by humans. Now, that's not to say there have not been other calving events of that size, but this is the first one we've been able to get on film. How big is it? Well, for those that are familiar with the East Coast, surface-wise, it was about the same size as Manhattan. Fell off of this glacier, and essentially the ice just went out in the ocean and will melt and be gone. So how do they work? Well, this is a great diagram I found. The first one on the left is showing the budget. So we have the zone of accumulation, which is your gains, and then your area of ablation, which is your losses. We know this occurs because as you get higher in elevation, looking up into these mountainous regions, it's colder. We know that because of the adiabatic lapse rate, and the closer down towards the surface, the warmer it will be. So we have gains versus our losses, and then we usually have a line, an equilibrium line or snow line, that we can significantly see that difference. All right, so what does this mean here? Well, the first thing we have is sublimation, which is something you remember. That is the act of ice turning directly into a gas. So it's part of melting. We have accumulation that's occurring here, and then we have calving events that cause the ice to break off and float into the oceans. Well, moving from this diagram over to this one, I thought this was really neat because this is showing what ends up happening. Here's your classic snow crystal. This is very dry. As you can see, it's 90% air, so this would be a great representation of firn. As it begins to granulate or get compressed, it starts to lose its crystalline shape, and you start pushing some of the air out. Then if it's able to withstand a whole year, we call it firn. And then we wrap up with glacial ice. Sorry, my nose itches. Which is where you have now about 20% of the air remaining. But this is your traditional glacial budget, and then looking from snow up to here, and as under its own pressure and time, as it gets down to this point, we're looking more at this firn and glacial ice. All right. Well, there's three types of bodies of ice that we can identify. We have or glaciers in that sense. I break it up into alpine, ice fields, and then ice sheets. So alpine glaciers are the things that we're most familiar with. So this photo here of Lake Sabrina, again, this is an alpine glaciated topography. So it's the types of glaciers that have been kind of constrained to their mountain peaks and areas where they originate from. The lowest reaches are usually bodied or surrounded by moraines. We'll talk about these terms in a moment. So alpine glaciers, think of of mountains like the Alps. Ice fields, the occupied highlands, they're usually quite large. They can even cover large landscapes. So I like to think of regions when I think of ice fields. When you think about a large region covered, it's probably an ice field. But if we get an ice sheet, I think continental. We're talking about incredibly massive amounts of ice that have been can cover landscapes and mountain ranges and everything like that, and will cover an entire continent. So, we can argue that for Yosemite, most of it was probably part of an ice field that was within that, near the bottom part. You also would have had some alpine glaciation that occurred higher up in the peaks. But you can start to see, okay, here we're looking at mountains, very large regions, and then even continents. We can break it into these parts. So I found this diagram. I thought this was kind of neat. This is kind of like a putting it all together. So it says what's within a glacier. So I'll start over here. So a glacier, they start in high valleys or mountains. They accumulate snow, and then under their own weight and gravity, they actually push and they actually move downward. And not all glaciers move at a rate that's observed by humans, and we can't just sit there and watch it. But there are some. The Jakobshavn Glacier is one that is the fastest moving. It's moving some between 20 and 30 meters a day. So you could actually almost watch it move. We see in this diagram here that the friction between the ice and the ground underneath controls as it carves. So this ice, as it's slowly moving towards us, you see these scratch marks. These are called glacial striations because the ice, the glacier itself, is obviously water, but whatever else was frozen. So since most of these took place in river systems, all of these rocks and cobbles get trapped along the bottom, and as that glacier is advancing, it's actually scratching and scouring the landscape underneath it. As the glaciers flow towards the sea, where they end up as icebergs after many years on the move, the glacier can also what we call retreat, where it melts back, leaving behind these very large lake deposits, leaving behind what we identify as moraines. Moraines is a fancy term for glacial material that got moved and deposited. I'll talk more about that in a moment. But this is kind of like putting it all together. So we're looking at everything at the top, everything at the bottom. As we see here, most glacial environments like this, take place or replace river environments themselves. The big difference, though, is that we find that rivers, they usually round out, though, especially when you get to old age, but they're really a V shape. They incise in the bottom or wherever that energy is the strongest. What's interesting with glaciers is that as that water expands, it usually pressures out. So it makes more of a very deep U shape as it carves along. So rivers make V's, and then glaciers usually carve like a U. So I mentioned some features. So here's a little diagram thing I want to show you. These are just some features that are found. And these are particularly done through erosional processes. So we've got cirques, arêtes, cols, harns, a head wall, glacial trough, hanging valley, glacial striations, and glacial polish. So these are some very important terms to know. I'm not going to be able to explain all of them. I'm going to explain a couple of them to try to get you going, but to make sure that you fill in the rest of the terms. So I'm going to start with a cirque because I've made reference of that before. We can see that this little cartoon is showing a cirque here. A cirque, it's French for amphitheater. So when I think of cirques, I think of Cirque du Soleil. A cirque is really the birthplace of an alpine glacier. It's the first place to freeze, last place to melt. Looking back at those photos of Lake Sabrina, I point out that big rounded bowl shape. That is a cirque. When I think of cirques, I think of ice cream. So here's a little animation I found. This guy's got an ice cream scoop, and if I hit play, you see how he's scooping away that ice cream. So the first place he's scooping from, that would be your cirque. That is the birthplace, of that glacier. So perhaps you have a small lake that would have existed first, and then it accumulated with snow over decades and decades and decades. As it continued to expand, the glacier, or this metal thing here, begins to push that material downhill. In this process, on either sides of the glacier, the glacier itself within the cirque, you see these little ridges on either side. Those are going to be your arêtes. Your arêtes are carved by glaciers going through. So imagine you scoop one scoop here, and you do another one next to it and left that little ridge in between. That ridge is an arête, or arête. It's French for a blade-like hill, or it's blade-like, like a knife. You'll also get peaks that have been carved because of cirques, so we call those horns. Perhaps you know one, like the Matterhorn. The glacial trough is this whole now big area down here. This is an example of that. This is a big glacial trough. What's interesting is you see this little drainage area that was probably a tributary to a river that used to exist down here, but now it's turned into a waterfall. So this valley is literally hanging above this one because all the glacier material moved and dug this whole area out, making a waterfall. Well, because that's a waterfall, this valley is hanging above this one. We call those hanging valleys. And you see how smooth this looks? This is smooth because of the striations and the polish. Glacial polish is like a turtle wax. So you have very fine-grained material that's between the ice and that surface. And as that glacier is sliding along, it actually polishes the rock material, making it very, very smooth. So to kind of put things in perspective real quick, I pulled this video up. We're going to go visit Lake Sabrina real quick. So we're going to zoom in any moment, starting now. No, did I hit play? There we go. So we're zooming into Lake Sabrina, right outside of Bishop. Oh, I lied. This is Convict Lake. I'm such a dork. It's another cirque itself. So Convict Lake is also, it's right north of Lake Sabrina. So what's interesting in this diagram here is I'm kind of panning out. So this is a glacially formed lake. Within that lake, you can see this bowl. That bowl is going to be the cirque. I'm zooming away from that so you can see that big rounded out area. You'll start, so now you can clearly see this nice large cirque. Here is an arête on this side here. We have some very dominant horns that have been seen. What's interesting is this right here. I don't know if I can just pause. These right here, look at these lines. Weird, right? There's like 1, there's 2, 3, 4, 5, maybe 5 or 6. In fact, you know, going back to that animation with the ice cream, maybe I scooped my ice cream out and I went down this way. Well, these are called moraines. I think of moraines much like you do it at the beach. You sit down at the beach and you push the sand away from you, right? When you push the sand away from you, some of that sand will be pushed to either side, making a ridge. Well, that's what these are. These moraines, this material was once up in here, but it's been pushed out. So this diagram here is actually showing us, zoom, 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 that the glacier that was here, oops, sorry, I moved it, has advanced, retreated, advanced, retreated, advanced. So you would see at least 3, 4, maybe even 5 different, advancements for this glacier. Now, if you were on a little, this is 395 heading up toward Mammoth, is like literally right up here. If you were driving up this way, heading off on this road, you would think these were small mountains, but they're not. What's interesting about them is when you get closer to them, you'll see that this material looks actually a little bit sorted in a sense, but not quite. But there's what we call erratics on it. And an erratic means like an erratic driver. It's all crazy. There's these large boulders that have been thrown here because as the ice moved all the material, it didn't sort it very well. It just layered it throughout its transport, but it just kind of dumps everything on its sides. So we're able to see that. Well, what about depositional features? Well, I just mentioned one for you. We've got moraines, lots of different types. We'll talk about those in a moment. Drumlins, kames, eskers, outwash plain, and then I mentioned erratics. So I'll start up here with a drumlin. The definition of a drumlin is an asymmetrical hill made of glacial till. So when I think of a drumlin, if you double it down below, it looks like a chicken drumstick, kind of, right? So it's like a teardrop shape in a sense. You have a long side and a short side. So the ice was moving from left to right. You have this bedrock that wouldn't move, this parent material, and then all of this glacial till, which is a fancy word for glacial debris, gets stuck on top of it as the glacier is within motion. So leaving behind these large drumlins or drumsticks. And again, these are quite large. A drumlin could be easily the size of a football field. Here we have some moraines. Here's the glacier moving towards us. The terminal moraine or the end moraine is where the glacial ended. The moraines on the side we find are lateral moraines because they're on either side. They're lateral. Looking at here, this is the definition of an esker. Here you have a glacier. Then and then you have some subglacial tunnels, which is essentially drainage. So there's a little bit of space underneath where the water from the ice is draining through and making an ice cavern. Well, now that that hole is available, a lot of material that was stuck within transport gets deposited and fills in that gap and creates this sinuous ridge. These sinuous ridges, I mean, if you think about it, looks like a river system, right? But then you get to look at it, like, wait a minute, no, it's up. Rivers do this, right? And it makes that river channel. Well, eskers are essentially like this, and they fulfill that river channel. So I like to think of them as an inverted stream, but in the sense that it's actually, instead of being erosional like a river, eskers are depositional, so leaving that material behind. Kames are unique as well. They're pretty essentially large pieces of ice will calve off onto the landscape. When the ice melts, it drops all of that glacial material, all the dirt and rocks and stuff like that, and creates these large um, mounds, like a picture's mound, like a pile. Looking more at moraines, here are some examples. So here we have some glaciers coming in this way, some coming in this way. So here we have our lateral moraines. This one, as you can see, has been labeled as a medial. A medial moraine is two lateral moraines meeting in the middle. So imagine that both my hands are glaciers coming out of canyons. So this glacier is coming out this way. My pinky and my thumb would be your lateral moraine. Here's another one, two lateral moraines, and they're merging in. They touch, boom, they crash into each other, where they, like two tributaries are joining in a river system. So two glaciers meet in the middle. Well, by meeting in the middle, you create a medial moraine. This is your terminal moraine, or the terminus, where the glacier, the farthest extent the glacier ever went. These are also end moraines, because what in this situation, the glacier must have advanced, the farthest extent it ever went, melted back, came forward, melted back, came forward, and made these other end moraines. The last end moraine is called a recessional moraine. I compare recessional moraines like receding hairlines. The hair was here, but now it's up here. It's been receding. So this is where it used to be, but this is where it currently is, right? So this is an example. Again, here's a horn. There's some arêtes. I'm not seeing very well-defined cirques in this area, but I'm sure they exist. This is a cartoon, right? But I mentioned some lakes, so let's look at some lakes. We have tarns, paternoster lakes, kettle lakes, ice-blocked lakes, and marshes and swamps. So this is an example of a kettle lake. Pretty interesting. Sorry, yeah. Well, it is a kettle lake. I'm going out of order. When I think of kettle lakes, I think of tea kettles. They hold water. So you essentially have glacial till that's been deposited. Ice either smashes into it or are stuck there. And as the ice melt, turns into water. Voila, instant lake. These are only found on the bottom of a glacier, way out. So we're looking more towards the terminus. So this is not up in the mountains. This is way down below. Now, a tarn is a glacial lake up in the mountains, up in that alpine environment. So looking at photos of Convict Lake, or looking at photos of Lake Sabrina, you have the cirque is the bowl around it, and the tarn is the soup within the bowl. It's the lake within that cirque. Paternoster lakes, pater meaning father, this actually makes reference to rosary beads. So when you have a bunch of rosary beads on a bracelet or one of the hanging elements, you've got all the different beads that are connected on that chain. Well, that's what a paternoster lake system is, that you have a tarn and all these other additional lakes. We often find that paternoster lakes are the result of moraines. So you have your tarn at the top, which is in your cirque, and then you can, as the glacier slowly melted back, it made these dams, these ice block dams that move that material with the moraines and made miniature lakes along the way. And then marshes and swamps are areas of poor drainage. A lot of information, I know. So let's play a game. This is an example quiz. Putting it together, right? So we've got some features. We've got K, L, M, N, O, P, Q, R, S, T, U, V. So here's a diagram. So we'll go through them very quickly, but here's K, L, M, N, O, P, Q, R, S, T, U, and V. So pause the video if you'd like and try to write down what you think they are. Okay? And then I'll see you in a moment. All right, well, welcome back. We'll zoom in here. We'll start off with letter K. K is a kettle. L is a terminal moraine. This is the farthest extent that the glacier went. We can see some of this unconsolidated debris as the glacier made its advancement. Letter M are drumlins, asymmetrical hills made of glacial tills. Letter N is a lateral moraine. It's on the side. There's one over here as well. Letter O is up here. Cirque, as it's dry, it's the shape, the amphitheater shape. P is this pyramidal peak. Q is this water, this lake within a cirque. It's called a tarn. R is an arête, a blade-like ridge carved between cirques. S is this additional lake down here. That's a paternoster lake, a chain of lakes. T is this ledge up here, known as a hanging valley. U is this sinuous ridge down here, known as an esker. And then V is this area out here, and that is the outwash plain. Well, I hope you did well, and I hope that you enjoyed this video as much as I did putting it together. Don't forget to subscribe and like to see my other videos, and we'll talk soon.